The Orion spacecraft, currently carrying the 4 crew members around the Moon, was built by Lockheed Martin and was named by its crew Integrity. It has roughly twice the mass of the Apollo Command Module, a habitable volume of just over 9 cubic meters in the crew module, and avionics systems that have no equivalent to anything flown in the 1960s. Its service module, which provides propulsion, electrical power, and life support, was built by Airbus Defence and Space for the European Space Agency, based on the architecture of the Automated Transfer Vehicle, ATV, that resupplied the International Space Station between 2008 and 2014. This is the first time in the history of human spaceflight that the service module of an American lunar spacecraft has been designed and built in Europe. The 4 astronauts forming the crew represent collectively a constellation of firsts that has no precedent in any single mission since Apollo 11. Reed Wiseman, Commander, 50 years old, a veteran of the ISS with experience flying in low Earth orbit. Victor Glover, pilot, 49 years old, the first African-American astronaut to undertake a lunar journey, who previously flew on SpaceX's Crew Dragon in 2020, and who during this mission becomes the first person of color to travel beyond low Earth orbit. Before launch, Glover publicly articulated something that is often left implicit in the narrative of space missions: that he preferred this milestone be seen simply as human history, not specifically Black history, because ambition should not be segmented by race. Christina Koch, mission specialist, 47 years old, who already holds the record for the longest continuous spaceflight by a woman at 328 days aboard the ISS, and who in this mission becomes the first woman to travel beyond low Earth orbit. Jeremy Hansen, mission specialist from the Canadian Space Agency, 50 years old, the first non-American citizen to make a lunar journey since the Apollo missions, the first Canadian to go beyond low Earth orbit, and in a sense, the representative of a category that no Apollo mission ever included: a lunar explorer from a nation that is not the superpower that financed the journey. The diversity of this crew is not accidental nor merely symbolic. It is the result of a deliberate programmatic decision to build the Artemis program as a genuinely international and representative enterprise. It is also, in practical terms, the clearest indicator of the difference between the political and cultural context in which this return to the Moon is taking place and the context in which Apollo occurred. Apollo was a race between superpowers. Artemis is, at least in its stated ambition, the first step toward a permanent human presence on the Moon, managed as a project of civilization rather than as a demonstration of national superiority. That change in framing has real operational consequences. Artemis II carries a scientific agenda that did not exist in Apollo. Not just a flyby and photographs of the surface, but systematic geological observations with high-resolution cameras, study of the solar corona during the eclipse from the far side, observation of lunar dust illuminated by Earthlight during the Earthrise, and space biology experiments with the Avatar payload, which uses bone marrow cells derived from blood samples of the crew to study the effects of deep space radiation and microgravity on human health. The spacecraft also has its own science console in Mission Control in Houston, the first time in NASA history that there is a dedicated lunar science command position integrated into the real-time operational flow of a crewed mission. The rocket that launched them is the SLS, 98 meters tall, and its 2 solid rocket boosters provided more than 3.2 million kilograms of thrust at liftoff, over 75% of the vehicle's total thrust. The April 1st, 2026 launch was, For many in the Cape Canaveral space community, the launch they had been waiting, delaying, and doubting for more than a decade. For the 4 astronauts inside the crew module, it was the flight they had been training for over years, knowing exactly what could go wrong, having read the mission risk assessments, having reviewed the Artemis I anomalies, having approved the mission profile with full awareness of everything contained within it. Pilot Victor Glover, upon regaining communication after launch, simply said, "We were surprised." He said it with a smile. Because in the mind of someone who has spent years preparing for a flight that might never happen, that could be delayed indefinitely, that carried the weight of an entire program on its outcome, expecting the rocket to lift off without issues, is different from believing that it will. It did lift off, and they have been in space for 6 days, and right now they are on their way back, with the flyby completed, the distance record set, and the re-entry that will test the heat shield that was not replaced just 4 days away. The question posed in the title of this video still does not have a definitive answer. November 2022. The uncrewed Artemis I mission completed its test flight around the Moon and returned to Earth with all systems apparently functioning. The Orion capsule splashed down in the Pacific Ocean, the parachutes deployed correctly. NASA held a press conference and spoke of new eras and historic milestones. Everything correct, everything within expected parameters. Except it wasn't entirely. In the weeks and months that followed the splashdown, as engineers subjected the recovered hardware to the kind of forensic analysis reserved for systems that are about to carry humans, they found something that shouldn't have been there. Orion's heat shield had eroded irregularly, not dramatically, not in a way that would have been visible from the outside or readable in telemetry data during the flight. But when they closely examined the physical surface of the recovered shield, it was there. Large fragments of the ablative material had detached in an unexpected manner. There were pockets of erosion that had penetrated deeper than predicted by thermal models. The ablative material, a substance called pave coat, specifically designed to burn away in a controlled and predictable way during re-entry, had not behaved as the simulations indicated. More specifically, there was evidence of gas entrapment. Bubbles had formed within the material during manufacturing or during the thermal cycle of re-entry. These bubbles created localized pressure points. The pressure caused cracks, and the cracks led to what engineers call spallation, fragments of the heat shield material physically separating from the surface during the moment of maximum thermal stress of the entire mission. There is one aspect of the problem that deserves to be emphasized because it defines the fundamental limit of what NASA could do about it. Orion's heat shield is not simply a larger version of Apollo's. At that scale, the thermal behavior of the ablative material enters a regime that had never been subjected to real re-entry conditions. The simulations were built on data from a different size range. The models predicted the behavior. The models were wrong. Not catastrophically. The capsule returned, and internal temperatures remained within acceptable limits, but in a way significant enough that no engineer responsible for flying humans could ignore it. Pause for a moment on what that means physically. During re-entry, the heat shield is the forward-facing surface of the capsule, the part that hits the atmosphere first. It is doing its job precisely by burning. That is intentional. Avcoat is designed to ablate, to sacrifice itself through a controlled combustion process that carries thermal energy away from the capsule rather than into it. The outer layers burn away. New layers are exposed. Those burn as well. It is a thermal sacrificial system, elegant in its simplicity, and it has worked on every crewed capsule, re-entry, in the history of American spaceflight. But spallation is not controlled combustion. Spallation is uncontrolled fracturing. These are fragments of material separating from the surface, not as a result of the designed ablation process, but as a consequence of internal mechanical failure. And once detached, these fragments are carried by the hypersonic flow around the capsule. Depending on their trajectory, they can impact other parts of the spacecraft. They can travel backward in the aerodynamic wake toward the parachute compartment, the very compartment that contains the only system capable of slowing the capsule from terminal velocity to a survivable splashdown speed. If debris from a heat shield that is breaking apart were to impact and damage a parachute before deployment, the resulting cascade of failures from that single event would have no recovery path. Charlie Kamada, a former space shuttle astronaut and heat shield specialist, was among the first to publicly articulate the magnitude of the issue. If he had to grade this heat shield from A to F, he said, he would give it an F. A clear F. Daniel Rasky, a retired NASA thermal systems engineer with more than 30 years of experience and co-inventor of the Pika material that later formed the basis for SpaceX's Pika X heat shield, was even more blunt. In his assessment, humans should not fly in such a system. NASA spent 18 months investigating the anomaly. It identified the root cause: gases trapped within the AV coat that did not escape quickly enough during the ablative process. It conducted additional testing, including evaluations of scenarios involving more extensive damage than that observed on Artemis I, and concluded that the underlying structure of the capsule would remain intact even under conditions beyond those expected. And it reached a conclusion that perfectly reflects the risk management philosophy defining this mission. Rather than replacing the heat shield, which would have caused significant delays and required another test flight deemed too costly, they modified the re-entry trajectory. A slightly steeper descent angle, less time at peak thermal load, lower probability that gas entrapment and spallation would recur at levels that could compromise the mission. It is an elegant solution in exactly the way engineering solutions tend to be elegant. It addresses the observable symptom with precision, without touching the underlying cause. The underlying cause is a material whose behavior at the scale of Orion is not fully characterized. The trajectory modification does not change that. What it does is reduce the exposure of the incompletely characterized material to the conditions that revealed its incompleteness. And here is the part that matters. A steeper descent angle reduces the duration of peak thermal exposure, but it also increases the intensity of the thermal load during the remaining window. You are compressing the same thermal event into a shorter period of time, which means the peak stress on the heat shield material, in terms of rate of temperature change, is higher than with the original trajectory. You have moved the risk, you have not eliminated it, and that distinction between moving risk and eliminating it is the most important concept for understanding everything else about this mission. Because that same movement of risk, that trajectory modification, also changes the conditions under which the parachutes deploy. The energy state of the capsule at the time it reaches deployment altitude is different from what the nominal design assumed. The parachutes were validated against nominal conditions, not against the modified ones. The risks are coupled. Pull one thread and another tightens. There is a system installed at the tip of the SLS rocket that generates approximately 180,000 kilograms of thrust in less than 3 seconds. It is called the Launch Abort System, and its purpose is to pull the capsule away from an explosion faster than a human can consciously process that an explosion is happening. The structure stands 13.4 meters tall and is composed of 3 solid rocket motors: the abort motor, which provides the primary extraction thrust; the attitude control motor, which orients and steers the capsule during the maneuver; and the jettison motor, which separates the abort tower from the crew module so the parachutes can deploy. All 3 motors were manufactured by Northrop Grumman. All 3 were tested individually on test stands and validated together in pad abort and ascent abort tests conducted prior to Artemis II. The abort motor also includes active lightning protection, since launches from Florida occur in a region with frequent electrical activity. The same protection system that routes lightning current safely away from the motor was developed in the context of this mission, and, according to Northrop Grumman, is already influencing the design of other rocket motors the company produces. To understand the thrust figure, consider this: the 2 solid rocket boosters of the SLS, each 54 meters tall, together generated more than 3.2 million kilograms of thrust at liftoff. The abort system, from a single rocket the size of a school bus, exceeds the combined thrust of a Boeing 747's engines. That disparity is not accidental. The system has to deliver all of that in a time window, measured not in seconds but in fractions of a second, because at the moment of a catastrophic rocket failure, it cannot wait for a human decision. It cannot wait for a flight controller in Houston to assess telemetry and press a button. By the time any human in the loop has consciously processed that something is wrong, the window for a successful abort will already have opened and may already be closing. The system is automatic. Sensors monitor the rocket's performance, and if they detect a signature consistent with a catastrophic failure, the system acts. No human in the loop, no confirmation. The decision is made by software in milliseconds. The crew is pulled away at up to 15 times the force of gravity. 15 Gs. For reference, fighter pilots in high-performance aircraft typically experience between 7 and 9 G during extreme maneuvers, and they train for years to maintain consciousness at those levels. The abort system subjects the crew to 15 Gs involuntarily, without prior preparation. Astronauts describe it as feeling like the weight of an elephant on their chest. You cannot breathe. You cannot move your arms or legs. Blood is forced toward the back and head, creating intense pressure in the eyes, ears, and internal organs. The entire sequence lasts only a few seconds. Those seconds are all that stand between the crew and a burning rocket. On launch day, during the countdown, one of the sensors in the controller of the attitude control motor battery in the abort system recorded a higher than expected temperature. The ground teams evaluated it over several minutes while the clock continued to run. They concluded it was an instrumentation issue, not a problem with the battery itself. NASA classified it as non-launch constraint and proceeded. The rocket launched. The battery was fine. That is, in miniature, what the abort system does throughout the mission: continuously monitoring, evaluating, distinguishing between real signal and noise. And that distinction between a genuine failure signature and a spurious sensor reading is the edge on which the entire value of the system rests. This is one of the counterintuitive truths of complex safety engineering. Safety systems do not reduce the total number of ways a mission can fail. They change the distribution of failure modes. They close some pathways and, by virtue of existing as additional complex hardware within the system, open others. Consider the full space of possible failures. If the abort system activates correctly during a real rocket failure, the crew survives. The spacecraft is destroyed. The mission is lost. But the 4 people are alive. That is the intended scenario. But the system can also trigger falsely. A sensor malfunction, a software error, an unexpected vibration signature from a perfectly functioning rocket that matches the profile the detection logic associates with structural failure. In that case, the crew is extracted from a rocket that was functioning properly. The mission is lost, but the crew is alive. Then there is the third scenario. The system fails to activate during a real catastrophic event. The sensors do not detect it, or the algorithm does not recognize the signature, or there is a hardware failure in the ignition system at the exact moment it is needed most. And finally, there is the fourth scenario, the one that lives in the most philosophically uncomfortable corners of the engineering design space. The abort system acts correctly. The motor ignites. The capsule is pulled away at 15 G. It reaches the peak of its abort trajectory. And then the separation motor, the secondary motor designed to detach the abort tower from the crew capsule before parachute deployment, fails to activate. The abort tower remains attached to the capsule. It is sitting directly above the parachute compartment. The parachutes cannot deploy through a solid rocket motor. The crew has successfully escaped the exploding rocket, and now they are in a capsule falling back to Earth without a functional parachute system. The abort system saved them from the explosion and delivered them into a different, equally lethal outcome. When you build a safety system, you are not making the mission safer in an absolute sense. You are making it safer in a probabilistic sense within the specific domain of failure the system was designed to address, while simultaneously introducing new failure pathways that would not exist if the system were not there. There is no lifeboat on Artemis II. Sit with that for a moment, because I think it is genuinely underappreciated in the public discussion of this mission. For the past 25 years, we have been operating the International Space Station, and during that time, the presence of a rescue vehicle has become so normalized as part of crewed spaceflight architecture that its absence is almost perceived as an oversight, rather than a deliberate design reality. At any given moment on the station, there is at least one Soyuz or Crew Dragon spacecraft docked to the structure, ready to undock and return the crew to Earth in an emergency. The presence of that vehicle does not change the probability that something will go wrong on the station, but it completely changes the space of possible responses when something does go wrong. And that difference between having options and not having them is not directly quantifiable in a risk assessment, because its value is not in how often it is used, but in what it enables. The possibility that an emergency becomes a problem to solve, rather than an inevitable outcome. Apollo 13 also had a lifeboat, although it was never designed to be one. The lunar module was built to land on the Moon and carry 2 astronauts back to the command module waiting in orbit. It was not built to serve as an emergency survival vehicle for 3 people during a 4-day return from the Moon. Its carbon dioxide scrubbing system was not sized for 3 people. Its power budget was not designed for the extended operation required in the emergency. The team on the ground had to design, in real time, an adapter for a filter cartridge using materials available on the spacecraft, because the square cartridges from the command module did not fit the round receptacles of the lunar module. They solved it with a plastic bag, duct tape, and the cover of a flight manual. None of that ultimately mattered, because the lunar module was there, because it existed, because the mission architecture included a second vehicle with its own independent power systems, its own propulsion, and its own life support. And when the oxygen tank in the service module exploded, the crew had somewhere else to go. Artemis II does not have a second vehicle. There is no tunnel to crawl through. There is no backup power system in a separate hull. There is no redundant propulsion in another spacecraft that can be brought online in an emergency. There is one spacecraft, 4 astronauts, and a trajectory defined by the laws of orbital mechanics. The free return trajectory provides what NASA describes as a passive safety mechanism. If the main propulsion system of the service module fails after the translunar injection burn, the geometry of the free return path means the spacecraft will continue around the Moon and curve back toward Earth without requiring any additional thrust. Gravity does the work, but the free return trajectory is not a rescue system. It is a return mechanism. And that distinction matters enormously in practice. That mechanism brings you back to Earth, in all scenarios, including those in which the spacecraft is not in a condition to survive arrival. If the heat shield has been damaged, if the parachute system fails, if the power systems have degraded to the point where the guidance computers cannot properly execute the entry sequence, the free return trajectory still brings you back to Earth. It does not help you survive the arrival. Physics is not a backup system. Physics is the only system. And physics, unlike a Soyuz capsule or a lunar module, cannot be updated mid-mission. It cannot be rebooted when it is not behaving as expected. It cannot be called from mission control when the situation changes. It is fixed. It is the consequence of decisions made before launch and committed into the geometry of the trajectory, and from that point on, completely beyond the reach of human intervention. There is something else worth saying about the absence of a lifeboat, something that is usually omitted in direct comparisons with Apollo 13. The lunar module, in its improvised role as a survival vehicle, was inhabited by 3 people for 4 days at temperatures that at times dropped below freezing inside the spacecraft. Interior surfaces became covered in condensation when the crew returned to the command module for re-entry. The astronauts reached splashdown, dehydrated, hypothermic, and physically weakened. They survived, but the system that saved them was operating at the absolute limit of its design capabilities, under conditions it was not built for longer than its engineers had ever intended it to function. The lesson of Apollo 13 is not only that backup systems can save lives. It is that backup systems can save lives even when they were not designed for the scenario that actually occurs, so long as they exist. The absence of that second vehicle in Artemis II is not a minor technical decision. It is a mission architecture decision that eliminates an entire category of possible responses to emergencies that cannot be predicted because they are not known in advance. That is precisely what it means to say that Artemis II replaces rescue capability with deterministic orbital mechanics. What no engineer can hear. For approximately 40 minutes during the Artemis II mission, the Moon stood directly between the crew and the Earth. On April 6, 2026, at 6:44 p.m. Eastern Daylight Time, Mission Control in Houston lost communication with the crew exactly as planned. The Deep Space Network, a system of 3 giant radio telescope complexes located in California, Australia, and Spain, specifically designed to maintain contact with spacecraft at interplanetary distances, remained pointed at the Moon in silence. It wasn't broken. There was no technical failure. The problem was geometric and absolute. The Moon is 3,474 kilometers in diameter. It has no atmosphere to scatter signals around its edges, and at that moment it sat directly between the spacecraft and every antenna on Earth. At 7:25 p.m., 41 minutes later, when the spacecraft emerged from behind the lunar limb, the signal was reacquired within seconds. Christina Koch's first words upon regaining contact were, "It's wonderful to hear you again." Those words represented everything Mission Control knew about the crew during that interval. That they were alive, that they had made it through. The moments that occurred within that window are now part of the mission's historical record, but for 40 minutes, they were not known to any human being on Earth. Every radio signal Mission Control sends to the spacecraft travels in a straight line at the speed of light. Radio waves do not bend around the moon. And when the spacecraft passes behind it, the electromagnetic connection between the crew and every human on Earth is physically interrupted. Not degraded, not weakened, interrupted, gone. For 40 minutes, Mission Control cannot hear them, cannot see their telemetry, cannot send commands, cannot warn them, cannot help them. The most sophisticated ground support infrastructure in human history becomes, for 40 minutes, a collection of very expensive antennas pointed at a rock. NASA Administrator Jared Isaacman downplayed the event in remarks to the press, describing it from Mission Control as fairly routine, noting that communication losses occur even in low Earth orbit missions. And technically, he is correct. The blackout was expected, planned, built into the mission timeline. The crew prepared their scientific observation schedule for the far side in advance, so that the time behind the moon would be fully utilized, regardless of communication status. It was not expected that they would need to ask for help. It was not expected that they would need to warn anyone of anything. But pilot Victor Glover, before launch, said something very different about those same 40 minutes. "I would love for the whole world to be praying that we regain signal and get back in contact." That is not the description of something routine. It is the description of something expected to go well, with the recognition that the phrase "go well" carries real weight. Only 27 people in all of history have passed behind the moon, all of them during the compressed window of the Apollo missions that ended in December 1972. Their descriptions of the moment when Earth disappears behind the lunar limb, when the constant chatter from Mission Control that has been present since launch gives way to complete silence, are remarkably consistent in their emotional tone. It is not exactly fear. Fear has an object. What Apollo astronauts describe is something more fundamental, the recognition of a kind of isolation that has no terrestrial equivalent. You are not merely far from home. You are in a place where home cannot perceive you, and you cannot perceive home. Michael Collins, orbiting the moon in the command module of Apollo 11, while Armstrong and Aldrin were on the surface, described the passage over the far side as the deepest solitude he had ever experienced. Even so, Collins was separated from the nearest humans by only a few hundred kilometers. The crew of Artemis II reached a distance of 252,756 miles from the nearest human being, with the moon blocking the line of sight. On Christmas of 1968, Apollo 8 became the first crewed spacecraft to orbit the moon. At the end of its 10 orbits, the crew ignited the engine to break orbit and begin the return to Earth. That critical maneuver was executed during the farside blackout. No one on Earth knew whether the engine had worked. Confirmation came only when the spacecraft emerged from behind the opposite limb and Frank Borman was able to report success. For those in Mission Control that night, those minutes of waiting were indistinguishable from the outside, from the alternative scenario. That structure of asymmetric uncertainty, where Mission Control has no information but the astronauts do, is the real operational challenge of the blackout. Not the psychological dimension of isolation, During those 40 minutes, the Artemis II crew was not resting. They were working. At 7:02 p.m., within the blackout, the spacecraft reached its closest approach to the lunar surface, at about 4,067 miles. At 7:07 p.m., also within the blackout, it reached its maximum distance from Earth for the entire mission, 252,756 miles, the farthest any human being has ever traveled in the history of our species. Wiseman and Hansen later reported that during those silent minutes, they observed 4 meteorite impacts on the lunar surface, brief flashes across the terrain that would later send the mission's science team into literal excitement in the evaluation room. None of that reached Earth while it was happening. The observations were made, the data was collected, the historic distance record was achieved. And Mission Control learned about it approximately 40 minutes later when the spacecraft emerged from behind the lunar limb and the telemetry link was restored. 40 minutes is an enormous amount of time for a spacecraft to be experiencing any kind of uncommunicated condition. To understand just how enormous, the most useful comparison remains. Apollo 13. From the initial explosion to the crew's first words to Mission Control, only seconds passed. The real-time collaborative loop was central to that crew's survival. Every decision that saved those 3 people was made in a context of continuous information flow. On Artemis II, during the far side passage, that loop does not exist. Whatever happens, happens. Any decision that is made will be made by 4 people with the training they brought with them, the data from their own instruments, and nothing else. But there is something more to add, something that is often missing from coverage of the blackout. The crew used that time with an efficiency that has no precedent in the history of space exploration. They had a schedule of lunar observations prepared for the hours before and after the far side pass, the first time in more than 50 years that human eyes observed the moon's geological features from that proximity. Wiseman photographed the surface with his iPhone. Hansen described over radio, after reacquiring signal, the view of a solar eclipse from the far side, the moon fully backlit, its entire surface glowing with refracted light around its edges, the sun gone behind a dark disk while the solar corona emerged as a perfect halo. While they were at the most isolated point in human existence, they were doing science. That, too, is part of the record of what was accepted. This is the part of the conversation where we need to talk about August 1972. Not as a historical curiosity, but as a warning directly relevant to what 4 astronauts are experiencing right now. The Sun is a variable star. That sounds like jargon, but it means something specific and consequential. The Sun does not produce energy at a constant rate. It breathes, in a sense, on a cycle of approximately 11 years of activity. At the bottom of the cycle, the solar minimum, the Sun's surface is relatively quiet. At the peak, the solar maximum, its magnetic field is at its most tangled, most stressed, most energetically active. Sunspots multiply, solar flares erupt, and most importantly, for anyone operating outside the protection of Earth's magnetosphere, coronal mass ejections occur more frequently and with greater intensity. The period from August 2nd to August 11th, 1972, produced what solar physicists consider one of the most powerful sequences of solar particle events ever recorded in the space age. The event was so intense that the high-energy particles it emitted detonated thousands of US naval mines deployed in Haiphong Harbor during the Vietnam War, causing spontaneous explosions that puzzled both sides of the conflict for days before the cause was identified. That is not a metaphor for the energy involved. That is what that solar storm did to explosive military devices sealed underwater on Earth, where the magnetosphere had already absorbed most of its intensity. Outside the magnetosphere, in transit between Earth and the Moon, the estimated radiation dose a crew would have received during the peak of that event ranges, depending on the analysis, from severe radiation sickness to potentially lethal exposure for at least some members of the crew. The event occurred between the missions of Apollo 16 and Apollo 17. The gap between an active crewed mission and a particle event capable of killing them was 45 days. Not an engineering margin, a coincidence of timing. Artemis II launched on April 1st, 2026, directly into a period of elevated solar activity. On March 30th, 3 days before launch, the Sun emitted an X-class flare, the most powerful category known, followed by a coronal mass ejection directed toward Earth. The NOAA Space Weather Prediction Center issued a moderate geomagnetic storm watch for March 31st. NASA determined there was no direct threat to launch and proceeded. The Sun was not yet quiet. What makes Artemis II qualitatively different from Apollo in this specific respect is not just the monitoring infrastructure, though that difference is real and substantial. It is the sophistication of the response system built around that infrastructure. The NASA Space Radiation Analysis Group, based at the Johnson Space Center in Houston, monitors the energetic particle environment in real time throughout the mission. The Moon to Mars Space Weather Analysis Office provides continuous assessment of solar activity. The NOAA Space Weather Prediction Center, with its network of geostationary GOES satellites, supplies real-time solar monitoring data that feeds predictive models. In Mars orbit, the Perseverance rover was even used as a solar sentinel during the period before and after launch. Because Mars was positioned on the opposite side of the Sun relative to Earth, its Mastcam Z cameras could observe sunspots up to 2 weeks before they rotated into view from Earth, providing an unprecedented early warning system. For this mission, NASA also incorporated 2 new predictive models developed by the University of Michigan. A machine learning model trained on solar and coronal images dating back to 1995, capable of estimating the probability of a solar particle storm up to 24 hours in advance, and a physics-based model that estimates radiation severity once an event begins. The data comes from 2 spacecraft: the Solar Dynamics Observatory, which images the Sun's magnetic field in visible and ultraviolet light, and the Solar and Heliospheric Observatory, which monitors the solar corona. Together, these systems can detect the precursor signatures of a coronal mass ejection before the plasma even leaves the Sun's surface. 6 HERA sensors, hybrid electronic radiation assessors, are distributed throughout the Orion crew module, measuring dose and dose rate in real time. The astronauts also carry personal active dosimeters. The European Service Module incorporates upgraded versions of the German DLR's M42 sensors that flew on Artemis I, with 6 times the resolution to distinguish between different energy types. All of this hardware produces a picture of the crew's accumulated exposure with a level of granularity that Apollo astronauts simply did not have. If the sensors detect an anomalous increase in particle flux, the system triggers an alarm. The crew moves to the designated radiation shelter, not a separate shielded room, but a defined area within the capsule where they can position themselves to maximize the material between them and the incoming flux, using the spacecraft's structure, stored water and food supplies, and equipment in storage bays as additional shielding. The operational principle is straightforward. Once the crew adds mass between themselves and the most exposed parts of the capsule, they can continue their normal functions. But consider the scenario at the intersection of two separate vulnerabilities. If a major solar particle event begins while the crew is behind the moon, if the onset of the storm falls within that 40-minute blackout window, Mission Control has all the information. The monitoring system is active. The alert would be sent immediately if the link were active, and the crew has no way to receive it. The spacecraft's instruments can detect the beginning of the particle flux increase. But here is the physics that makes this genuinely uncomfortable. The most dangerous solar particle events have a characteristic time structure. The highest energy particles, the protons traveling at a significant fraction of the speed of light, arrive first as a relatively brief precursor to the main wave. This precursor is the warning. If you recognize it quickly, you have some time. That advance warning is measured in minutes. If the crew is executing a navigation burn, or managing an unrelated system anomaly, or dealing with any of the other operational demands of the Farside Pass, then, at the moment, the radiation monitors begin to register anomalous readings. If no one is looking at that specific display at that moment, the response window compresses, the precursor passes, the main event arrives, and the shelter position that could have significantly reduced the dose becomes less effective with every additional minute of exposure that occurred before the crew reached it. In Artemis II, that intersection did not materialize. The sun behaved during the 40 minutes of blackout. But the condition that makes that intersection possible was not eliminated. It was accepted as part of the mission's risk profile. Radiation is the most philosophically unsettling danger of the space environment, and it's worth pausing to understand why. It's not just the biological hazard, it's the complete mismatch between the nature of the threat and the sensory equipment humans evolved to detect threats. That mismatch has real operational consequences, and understanding it is essential to understanding why radiation management in deep space is qualitatively different from almost any other risk astronauts face. Every physical danger that shaped human evolution over millions of years announced itself through the senses. Fire is visible and hot. A predator makes noise and movement. A fall has the sensation of acceleration before impact. Deep water exerts pressure. Extreme cold produces pain before numbness. Even chemical dangers in the natural environment, plant and animal toxins, often have smell or taste as warning signals, and many trigger immediate physical reactions that clearly communicate that something has gone wrong. Human biology is exquisitely tuned to detect and respond to threats that interact with the physical world in ways that produce sensory information. The nervous system, from the simplest pain receptors in the skin to the most complex sensory integration circuits in the brain, is essentially a threat detection system built for the terrestrial environment. It worked extraordinarily well over millions of years of evolution in that environment. It was not designed for space. Ionizing radiation produces no sensory information at all at the dose levels relevant to a solar particle event or to cumulative exposure in cislunar space. You cannot see it. You cannot hear it. You cannot feel it. You cannot smell it. There is no sensory receptor in the human body that responds to high-energy protons, gamma rays, or heavy galactic cosmic ray particles with any signal the brain recognizes as, "There is something here that is harming me." High-energy protons from a solar particle event pass through the walls of the spacecraft, through the bodies of the crew, through everything inside the vehicle at a significant fraction of the speed of light, depositing energy in biological tissue through ionizing interactions that are completely below the threshold of human sensory detection. Ionization happens. DNA strands break, proteins are damaged, cells die or mutate, and the organism does not know. Not in the way it knows when you cut a finger or touch a hot stove. There is no immediate alarm signal, no reflexive withdrawal, no message from the nervous system that communicates to consciousness that something is happening. There is one phenomenon astronauts report consistently, a partial exception, the only crack in that total invisibility. Flashes of light inside the eyes, even with eyelids closed. They are caused by high-energy particles passing through the retina or optic nerve, directly stimulating photosensitive cells without any actual photons present. They are not harmful in themselves. They are not a warning about total dose. They are simply the perceptual signature of individual particles passing through a tissue that, because it is light-sensitive, produces a visual experience in response to sufficient energy input. Astronauts from Apollo reported them. Astronauts on the ISS report them. And they are unsettling precisely because they are the only signal of something the senses were never meant to detect. A tiny, indirect window into a process occurring throughout the entire body simultaneously that the nervous system cannot directly report. The first indication that something significant has happened may come hours or days later. Nausea, unusual fatigue. In more severe cases, hair loss, immune suppression. Acute radiation syndrome, the most severe form of high-dose exposure, begins with what physicians call the prodromal phase, nausea, vomiting, diarrhea within the first hours. It progresses to a latent phase, where the patient may feel better for days while the bone marrow is being silently destroyed. And then comes the manifest illness phase, when the immune system collapses because new blood cells are no longer being produced in sufficient numbers. That temporal profile, the delay between exposure and symptoms, is operationally critical. It means that if a significant exposure occurs on day 6 of the mission, during the farside pass or at any other moment, the first symptoms might begin appearing in the final days of the flight, when the crew is preparing for re-entry and splashdown. Re-entry requires the crew to be alert, functional, capable of executing emergency procedures if something goes wrong with the heat shield or the parachutes. The cognitive degradation that can accompany acute radiation syndrome, even in its milder forms, is not compatible with that level of operational demand. Dr. Tara Castleberry, Associate Professor of Aerospace Medicine at the University of Texas Medical Branch and a flight surgeon supporting the Artemis program, framed the long-term consequences with clinical precision. Exceeding lifetime cumulative exposure limits for astronauts increases the risk of cardiovascular disease, long-term cognitive decline, and performance degradation. Those limits are individualized, calculated based on each astronaut's exposure history, and they are finite. Once exceeded, eligibility for future flights is re-evaluated. That constraint is not bureaucratic. It reflects the physical reality that radiation damage is cumulative, irreversible, and largely indistinguishable from normal aging processes in its long-term effects. The Artemis II crew spends more time in the Van Allen radiation belts than Apollo crews did. The Artemis II trajectory, which includes a long orbital arc around Earth before the translunar injection burn, passes through the belts with a longer exposure duration than the direct insertion profiles used in Apollo missions. The Van Allen belts are toroidal regions of charged particles trapped by Earth's magnetic field, an inner belt dominated by high-energy protons and an outer belt of electrons, and traversing them on both outbound and return legs adds to each astronaut's cumulative lifetime. Dose: a small Korean CubeSat, KRAD cube, launched alongside the mission, was designed specifically to measure radiation effects on human tissue during passage through the belts, adding high-resolution scientific data to what the spacecraft's own sensors are already recording. There are 3 sources of radiation the crew is exposed to outside Earth's magnetosphere. Galactic cosmic rays are particles of interstellar and extragalactic origin traveling at relativistic speeds, and they are essentially impossible to block with any reasonable amount of shielding. Their energy is so high that they pass through almost any material that can fit inside a habitable spacecraft. Exposure to galactic cosmic rays is constant, cumulative, and has no operational response beyond minimizing the total duration of the mission. Solar energetic particles, by contrast, are the acute risk, the kind that can cause biological damage on timescales of hours. And for that risk, there is a response. The shelter, the reconfiguration of the cabin to maximize shielding, the positioning of the crew in the part of the spacecraft where the most mass lies between them and the incoming flux. The effectiveness of the shelter system is real and measurable. Analyses conducted by NASA's radiation biology teams, based on data from the Helga and Zohar mannequins flown on Artemis I, along with simulations of solar particle events of varying intensity, show that the shelter configuration significantly reduces the dose received even in severe events. A useful analogy from NASA radiation analyst Stuart George captures the dynamics. It's not like being shot, it's like sitting in a bathtub that gradually fills with water. The particles arrive in bulk from all directions and the dose accumulates over hours. That means moving to the shelter 10 minutes after the warning is better than moving 30 minutes later. And moving the moment the high-energy precursor begins to register is better than waiting for mission control to analyze the data and send instructions. Managing that process in real time requires exactly the kind of sustained attention to radiation instruments that competes with every other operational demand of the mission. Astronauts cannot watch the radiation monitor constantly. They have tasks, they have experiments to run, they have systems to monitor. They have a lunar flyby they have spent years preparing specific observations for. And the instruction to watch the radiation monitor at all times competes directly with every one of those other instructions. The Avatar payload on Artemis II adds a scientific layer to the monitoring system. It uses organ-on-a-chip devices, functional human tissues grown in microstructures the size of a thumb, to study the effects of deep space radiation and microgravity on human physiology. The bone marrow cells included in the payload were derived from blood samples of the crew themselves. That means the data from Avatar is not just general science about how space affects the human body. It is data about how space affects these 4 specific individuals. That information will be used to refine radiation risk assessments for future missions. It also means that the crew is, in a more literal sense than usual, part of the experiment being conducted. The complete monitoring ecosystem NASA has built around radiation risk for Artemis II, from the Perseverance rover on Mars to the HERA sensors inside the cabin, from predictive models developed by the University of Michigan to the personal dosimeter in each astronaut's suit, represents an enormous quantitative and qualitative leap over what Apollo program had available. During Apollo, the absence of a lethal particle event was luck. In Artemis II, the absence of such an event may be luck, or it may be the result of a warning system that functioned correctly and simply had nothing to warn about. From the outside, those 2 possibilities are not always distinguishable. What can be said with certainty is this: the Artemis II crew is operating in an environment where the primary threat to their long-term health is completely invisible. completely odorless, completely intangible, and only detectable through instruments that must be actively checked to reveal what is happening. That condition, the threat that cannot be felt but can be measured, that cannot be avoided but can be mitigated, that produces no pain in the moment but may produce illness months or years later, is perhaps the aspect of deep space for which human biology is least equipped. And the technology available in 2026 represents the best response currently possible, which is not the same thing as a sufficient one. At 40,000 kilometers per hour, the Orion spacecraft approaching Earth for re-entry must enter the atmosphere at an angle between 5.5 and 7 degrees relative to the local horizon. Let that land as a number, shallower than 5.5 degrees, and the spacecraft doesn't meaningfully enter the atmosphere at all. At that speed, a shallow trajectory causes the vehicle to skip off the upper atmosphere, like a flat stone across water. The air is too thin to slow it down. Instead, it deflects the spacecraft back into space. And at those velocities, that bounce doesn't just delay arrival. It sends the spacecraft onto a new trajectory, potentially far from the planned recovery zone. Steeper than 7 degrees, and the atmosphere becomes dense enough at entry to generate aerodynamic loads and heating rates beyond what the spacecraft is designed to survive. The heat shield, the same one that already showed unexpected behavior, faces a thermal environment more extreme than its design envelope. Between those two outcomes, there is a margin of 1.5 degrees. Extend your arm fully in front of you and look at your little finger. The apparent width of your pinky at arm's length subtends roughly 1 degree of visual angle for an average adult. The entry window for Artemis II is about 1.5 times that, and you are trying to hit that window from roughly 400,000 kilometers away, traveling at 10 times the speed of a rifle bullet, on a trajectory that has been accumulating every navigation error introduced along the way. Under nominal conditions, the guidance computer handles all of this. Orion's guidance, navigation, and control system is far more sophisticated than anything that flew during the Apollo program. It continuously processes sensor data, calculates the spacecraft's state vector, its position, velocity, and attitude, and makes real-time corrections to keep the re-entry trajectory within that narrow corridor. But the guidance computer is an electronic system, and every electronic system operating in space is exposed to ionizing radiation. The same high-energy protons from the solar environment that pose a biological risk to the crew also pose a risk to onboard electronics. When a high-energy particle passes through a semiconductor memory chip, it can deposit enough charge in a single memory cell to spontaneously flip the stored bit from a 0 to a 1 or from a 1 to a 0. Engineers call these events single-event upsets or, more informally, bit flips. Most bit flips are detected. Modern radiation-hardened electronics use error detection and correction codes, extra redundant bits that allow the system to identify when a bit has changed and fix it without losing data. For the vast majority of events, this works. But a bit flip in a single memory cell storing a critical navigation parameter, if it goes undetected and uncorrected, can propagate into physical consequences. A guidance computer that believes it is targeting a 6-degree entry angle when it is actually targeting 4.5 degrees will fly a trajectory that skips off the atmosphere. The backup to a failed or corrupted guidance computer is, at its core, the same system used by Apollo crews and by navigators for centuries before the space age: celestial navigation. The crew can use an optical device similar to a sextant to measure the angular positions of known stars relative to the spacecraft's orientation and the Earth's limb. From those measurements, they can calculate the spacecraft's precise attitude and trajectory, and use that solution to correct the re-entry targeting manually. The mathematics behind it is sound. The technique works. It worked during the Apollo program. Crews practiced it as a backup and validated that it could replace the primary guidance system under failure conditions. But it requires time. It requires the crew to be in a physical and cognitive state where they can perform precise optical measurements and carry out the necessary calculations. And it requires that whatever failure condition made the backup necessary, whether radiation-induced corruption of the guidance computer, a software anomaly, or a hardware fault, has not also degraded the crew's ability to execute the procedure. If the failure condition that degraded the guidance computer was a severe solar particle event, and the crew has been exposed to radiation during that same period, then the question of their cognitive state, at the moment they need to perform manual navigation, stops being abstract. It becomes operational. In the most extreme failure scenario imaginable, corrupted guidance computer, crew managing radiation exposure, communications blackout still in effect, re-entry window approaching, the most sophisticated crewed spacecraft ever built, reduces to a human being with an optical instrument, measuring the angle between a star and Earth's horizon, performing the same mathematics that maritime navigators once carried out with sextants on wooden ships crossing unknown oceans. Space is not empty. That sounds obvious when you say it out loud, but the mental image most people carry of the space between Earth and the Moon is essentially a pure, featureless void. Darkness interrupted only by the occasional dramatic object. The reality is far more crowded and far more dangerous in a way that operates below the threshold of human perception and completely outside the reach of human response. Cislunar space, the volume between Earth and the Moon, is an active debris field. Not in the cinematic sense of large, visible rocks tumbling through darkness, but in the physical sense, a vast region populated by particles ranging from microns to meters in size, distributed across enormous distances, moving along trajectories shaped by billions of years of solar system dynamics. Impact velocities in this environment range from about 3 kilometers per second at the low end to roughly 70 kilometers per second at the high end. To make that meaningful, a 9mm handgun bullet leaves the barrel at around 370 meters per second. The slowest micrometeoroid impacts in space occur at speeds roughly 8 times faster than that. The fastest approach 200 times faster. You're not dealing with faster bullets. You're dealing with an entirely different physical regime of impact events. At those speeds, mass stops behaving the way it does in any impact scenario within ordinary human experience. Kinetic energy scales with the square of velocity, which means doubling an object's speed quadruples its energy. EK equals 1/2 mv squared. EK equals 1/2 mv squared. EK equals 21 emv squared. A particle the size of a grain of sand traveling at 40 kilometers per second carries kinetic energy roughly comparable to a rifle round. A particle the size of a small marble at the same speed delivers energy comparable to a hand grenade. These are not metaphors chosen for dramatic effect. This is the actual physics of what happens when small, fast objects meet the hull of a spacecraft. The Orion capsule is shielded against micrometeoroid impacts. Multiple layers of aluminum and other materials are built into the hull specifically to absorb and disperse the energy of incoming particles. It uses a Whipple shield design, named after astronomer Fred Whipple, where a thin outer bumper layer vaporizes or fragments the incoming particle, spreading its energy over a wider area before it can reach the main pressure hull. That shielding is designed around probability. It protects against the statistical distribution of the most likely impact events, optimized for the mass and velocity profile that represents the vast majority of debris in cislunar space. It is not designed to stop everything. It cannot stop everything. Designing a hull capable of stopping every possible object in the cislunar environment would require so much shielding mass that the spacecraft would be too heavy to launch. A micro-perforation, a pinhole breach in the pressure hull caused by a high-velocity particle that the shielding did not fully stop, produces a slow depressurization. The pressure differential between the cabin, maintained at roughly sea-level atmospheric pressure, and the vacuum outside, effectively zero, drives air through the opening at a rate determined by the size of the hole. A very small hole leaks slowly enough, potentially, for the crew's instrumentation to detect the pressure drop before it becomes physiologically significant. Orion is equipped with highly sensitive pressure monitoring, and the crew is trained for hull breach scenarios. A larger impact changes the equation in ways that do not scale linearly. A breach the diameter of a pencil decompresses the cabin far more rapidly than a pinhole. The crew's response time compresses from potentially minutes to potentially seconds. And a significant impact, one that penetrates not only the outer shielding and pressure hull, but also the underlying structural members of the capsule, introduces failure modes for which there is no response protocol. Because there is no response to a catastrophic structural failure of a pressure vessel in cislunar space. There is no patch. There is no repair procedure. The probability of a micrometeoroid impact during the Artemis II mission is low. The probability of a penetrating impact is lower. The probability of a mission-ending impact is lower still. All of those statements are accurate. They are also, in a very specific sense, beside the point. The universe does not consult probability tables before deciding where a given particle is on a given day. Probability tells you what to expect across a large number of missions. It tells you almost nothing about what happens on this mission to these 4 people during this specific transit. Low probability is a statement about a population of events. The Artemis II crew is not a population. They are 4 individuals, and for them, any given impact either happens or it doesn't. And once the particle is in motion, the probability that preceded it becomes irrelevant. If you're looking for the single moment in the Artemis II mission profile where the convergence of failure modes is most uncomfortable to contemplate, it isn't during transit. It isn't behind the moon. It isn't during the window of peak solar exposure. It's at the very end, after everything else, after the heat shield has done its job, after the re-entry corridor has been threaded at 40,000 kilometers per hour. The moment of maximum vulnerability in Artemis II is when 3 parachutes are supposed to open over the Pacific Ocean. The Orion capsule doesn't glide to a landing. It has no wings, no runway, no controlled aerodynamic approach. It falls. After re-entry, after the heat shield has shed the thermal energy of atmospheric entry and the capsule has decelerated from orbital velocity to something closer to terminal velocity at low altitude, the parachute system deploys in a carefully sequenced cascade. First, the drogue parachutes deploy to stabilize the capsule's attitude and begin deceleration. Then, the 3 main parachutes open, large enough that their combined canopy area covers roughly the footprint of a small office building, slowing the descent to a splashdown speed that both the capsule's structure and the crew can survive. 2 of the 3 main parachutes must work. That's the threshold. One failure is within the system's design tolerance. The remaining 2 parachutes can still bring the capsule down at a survivable speed. 2 failures are not tolerable. The descent rate with only 1 parachute exceeds what the capsule structure and the human bodies inside it can withstand upon splashdown. And here's the thing about the parachute system that ties it back to everything discussed before. The deployment conditions, the altitude, the velocity, the capsule's pitch angle, the aerodynamic loads it's experiencing at the moment of deployment are not independent of the decisions made earlier in the mission. The trajectory modification that NASA implemented to reduce thermal exposure on the heat shield changes the capsule's energy state during re-entry. A different energy state in re-entry means a different velocity profile through the atmosphere. A different velocity profile means the capsule reaches parachute deployment altitude in a slightly different condition than the one assumed in the mission's nominal design. The parachutes were tested and validated against nominal conditions. The real conditions will be the modified ones. None of this means the parachutes will fail. It means the conditions under which they deploy are not identical to those they were primarily validated against, because earlier conditions were changed to manage a different risk. The risks are coupled. Change one, and you change the environment the others have to operate in. And then there's the scenario that doesn't involve any catastrophic failure at all. No explosion, no micrometeoroids, no parachute failure. Just a burn that delivers slightly less than nominal thrust. A trajectory that diverges from the planned path by a fraction of a degree, so small that early telemetry doesn't flag it as critical. Accumulating over distance into a deviation that only becomes significant when it's already too late to correct with the remaining propellant budget. If the service module's main engine underperforms during the critical return burn, not a total failure that would trigger immediate emergency protocols, but something like 94 or 95% of nominal thrust over a slightly longer than planned burn, the geometry of the trajectory changes. The spacecraft reaches the moon's sphere of gravitational influence on a slightly different vector than intended. And instead of the free return trajectory curving it back toward Earth, the moon's gravity captures it. The spacecraft enters an elliptical orbit around the moon. It's not falling back to Earth, it's falling around the moon in a closed orbit that goes nowhere. The crew would know immediately. The telemetry would be unambiguous. Communication with mission control would be intact. This scenario doesn't involve the far side blackout. Mission control and the crew would share a complete picture of what happened and what it means. They would work the problem together, with every resource NASA's engineering infrastructure can provide. And at the end of that process, they would arrive at a number, delta V, the change in velocity required to escape lunar orbit and set a course back to Earth. They would compare that number to the propellant remaining in the service module after the underperforming burn. And if the numbers don't match, if the physics of the situation demands more energy than the spacecraft has left to provide, then the conversation reaches a point where the engineering options are exhausted. Earth would be visible through the capsule windows, a blue and white sphere roughly the size of a marble held at arm's length, about 384,000 kilometers away. A radio signal crosses that distance in about 1.3 seconds. The crew could talk to their families. They could talk to mission control. They could see with their own eyes the planet they came from and the planet they were trying to return to. And orbital mechanics would be indifferent to all of it. Proximity is not the same as accessibility in space. You cannot negotiate with a gravitational field. You cannot improvise your way out of a propellant deficit. Earth would be right there, visible, reachable by radio, and completely physically unreachable. And the gap between those two facts would be the entire story of what it means to be human in deep space with an insufficient delta-V budget. That scenario, quiet, slow, technically understood, survivable at the beginning, and unsurvivable in its conclusion, is the one that most cleanly illustrates what Artemis II has actually accepted. Not fire, not impact, mathematics. There's a question that comes up repeatedly in the comments on any coverage of Artemis II, and it sounds completely reasonable until you examine it closely. The question is this: if the Apollo astronauts went to the moon with computers less powerful than a pocket calculator, why in 2026, after decades of technological advancement, is the probability of losing the crew still around 1 in 30? It's a fair question. It deserves an honest answer. And that answer has several layers that run counter to most people's intuition about how technological progress works when applied to systems of extreme complexity. The standard intuition about technology goes like this: systems improve over time. Computers in 2026 are exponentially more powerful than those in 1972. Materials are more advanced. Simulation models are vastly more sophisticated. Instrumentation is more precise. Therefore, spacecraft in 2026 should be much safer than those in 1972. That logic is correct for many categories of systems. It's exactly what has happened with commercial aviation, where decades of incremental improvements in engineering, pilot training, warning systems, maintenance procedures, and regulation have driven the fatal accident rate per passenger kilometre down to levels that are statistically negligible. A commercial flight has roughly a 1 in 11 million chance of ending in a fatal accident. But that outcome didn't come from a single dramatic technological leap. It came from repetition, thousands upon thousands of flights, data accumulated over time, failures analysed, procedures revised, and an entire learning cycle that is only possible when the same basic system operates repeatedly under similar conditions. Human deep spaceflight doesn't have that cycle. It can't, not with the resources available to any space agency on Earth. Artemis II is only the second flight of the SLS and the first Orion flight with humans on board. Not the 100th, not the 1000th. The first. The statistical foundation needed to build a well-grounded probability of crew loss simply doesn't exist. And that's a problem that is structurally different from anything more computing power can solve. NASA's Human Exploration and Operations Chief, John Honeycutt, put it with a level of candor that's rarely heard in press briefings. I don't know exactly what the number means. What he meant isn't that engineers are careless or that they haven't tried to calculate it. It's something more fundamental about the nature of probabilistic risk assessments when the underlying data is sparse. To understand where the 1 in 30 number comes from, you have to understand what a probabilistic risk assessment, PRA, is and what it isn't. A PRA, in NASA terminology, is a systematic method to identify all the failure modes in a complex system, estimate the probability of each one based on test data, historical data from similar systems and engineering models, and then compute the combined probability of mission loss or crew loss by aggregating all those contributions. The result is a number, a probability. That number has the appearance of precision. It has decimal places. It's documented across hundreds of pages of technical analysis. And that appearance of precision is both its strength and its biggest source of misunderstanding. NASA began applying PRA systematically to the Space Shuttle after the Space Shuttle Columbia disaster. The results were revealing in ways no one had fully anticipated. Retrospective analysis concluded that the real probability of loss of crew per shuttle mission was about 1 in 85, with a confidence range spanning from roughly 1 in 123, optimistic, to 1 in 59, pessimistic. The actual historical outcome? 2 crew losses in 135 missions, about 1 in 67, squarely within that estimated range. The system worked in the narrow sense that the analysis was retrospectively consistent with reality. But there's something that analysis couldn't do. It was completed decades after the shuttle had already been flying. During the early flights of the program, in the 1980s, program managers had estimated the probability of crew loss at around 1 in 100,000. That estimate wasn't deliberately dishonest. It was the result of a mathematical model applied to individual component data in laboratory conditions, in the absence of real flight data. The gap between 1 in 100,000 and 1 in 67 isn't a story of bad engineering. It's a story about the limits of prediction, the behavior of a system of extreme complexity in real flight conditions cannot be fully inferred from its individual components, no matter how much computational power you apply to the models. The problem has a technical name: the unknown state space. In any complex system, there are failure modes engineers anticipated and modeled carefully. There are failure modes they suspected but couldn't quantify precisely due to limited data. And then there are failure modes no one anticipated because they hadn't happened yet. A probabilistic risk assessment can only include the first 2 categories. The third, by definition, is not in the model. And for a system that has flown only a handful of times, that third category can be the most significant of all. The heat shield anomaly from Artemis I illustrates this perfectly. It wasn't that engineers had never considered the possibility of issues with AVCOAT. The material had been studied, tested, modeled. Thermal analyses existed. Predictions existed. The problem was that the predictions were wrong in ways that only became visible after the real hardware flew under real conditions at full scale. The spallation wasn't in the model because the model was built on data from a different size regime. No amount of additional computing power fixes that without full-scale flight data, because the limitation isn't calculation. It's that the physical parameters at Orion's scale simply weren't fully known until Orion revealed them. Now consider what that means for the 1 in 30 number for Artemis II. That number is built on the most sophisticated technical analysis available, updated with Artemis I data, informed by 18 months of heat shield investigation, incorporating additional scenario testing NASA conducted before launch. It has been reviewed by external engineers. The NASA administrator read it, the astronauts read it, and chose to fly anyway. And the number remains 1 in 30 because that is the most honest estimate the current state of knowledge allows. Not because the engineers are incompetent, not because the materials are primitive, but because the system has flown once without people. Because there are coupled failure modes that only reveal themselves under real flight conditions with a crew on board. Because the behavior of life support systems over 10 days in deep space under real radiation exposure can only be fully characterized by actually doing it. And because the physics of deep space does not make exceptions for safety margins written into documents on Earth, there's a comparison that clarifies this better than anything else. NASA's Commercial Crew Program, regular missions by SpaceX's Crew, Dragon to the International Space Station, operates with a loss of crew threshold of about 1 in 200. not because Crew Dragon is inherently a safer spacecraft than Orion in any absolute sense, but because it has flown dozens of missions. It has an operational history that allows models to be calibrated against real data. Failure modes that could emerge in early flights have already emerged, been studied, and corrected. Engines have fired thousands of times. Parachutes have deployed repeatedly. The heat shield has been validated in real re-entries again and again. The 1 in 200 figure is not a guarantee that Crew Dragon cannot fail. It's an estimate informed by a volume of data that Artemis II structurally cannot have yet. Deep space adds a third dimension to this problem, one that no amount of low Earth orbit experience can fully resolve. The operational conditions are qualitatively different from anything these systems have faced before. Deep space radiation, thermal extremes, vacuum conditions, electromagnetic isolation during far-side blackout, the unique thermal loads of lunar re-entry. These are not environments that can be fully reproduced on Earth, nor fully captured in simulation, nor even approximated in orbital missions. They can only be truly characterized in the mission itself. That is not a failure of modern engineering. It's an honest description of the limits of pre-flight knowledge when dealing with systems operating in environments humanity has inhabited only 27 times in 53 years. The difference between 2026 and 1972, in this specific sense, is not simply that the technology is better, though in many ways it is. The difference is that in 2026, we understand these limits well enough to document them precisely, to quantify the remaining uncertainty rigorously, and to produce a number that reflects, honestly, both what we know and what we don't. The 1 in 30 figure is more honest than the 1 in 100,000 the Space Shuttle program claimed in its early years. That doesn't make it more comfortable to contemplate, but it does make it more useful for anyone who actually wants to understand what's happening out there. There's a second dimension to this problem that's worth examining directly, and it has to do with what an acceptable risk threshold actually means, in practice for the people who decide to fly. When NASA sets a loss of crew threshold of 1 in 30 for Artemis II, it's making a technical statement, the result of a formal risk assessment. But that technical statement has to be read and accepted by specific human beings who are going to get on that spacecraft. And this is where probabilistic language and human experience of risk diverge in ways that matter. A 3.3% probability of loss of crew means, statistically, that if you flew 30 identical Artemis II missions with the same spacecraft and the same risk profile, you would expect about one of them not to bring the crew home. That's what the number says. What it does not say, and what no number can say, is which mission out of those 30 it would be. For the individual crew, 1 in 30 does not function as a probability distributed across abstract missions. It becomes a binary question. Does this mission with these 4 people at this moment end well or end badly? Statistics describe populations. Astronauts are individuals, and for an individual, any given event either happens or it doesn't. The probability that preceded it has no operational value once the spacecraft has launched. So, what does 1 in 30 represent in practice? It represents a threshold of acceptance. It is the institutional formalization of a decision that the value of what this mission can achieve outweighs the expected cost of taking that risk, calculated as probability multiplied by consequence. In its most stripped-down form, it is an expected value calculation applied to human lives, written down, reviewed, and signed by people with the authority to do so. and there's something important about who signs that document and who reads it. NASA signs it as an institution through a process involving engineers, program managers, independent reviewers, and leadership. The astronauts read that number, understand its technical implications at a depth no outside observer can match, and then make a decision of their own, whether or not to fly. Reed Wiseman boarded, Victor Glover boarded, Christina Koch boarded, Jeremy Hansen boarded. None of them did so because they misunderstood the number. They did it with full awareness that 1 in 30 is not the same as 1 in 200, and that the gap between those numbers is not a temporary technical imperfection to be fixed on the next mission. It is an honest reflection of what can be known before flying a new system into deep space for the first time. Before launch, Wiseman said something in a press conference that didn't get nearly as much attention as the technical risk discussions. He said the crew had trained for years, that they knew the vehicle, that they understood the risks, and that they were ready to go. He didn't qualify the risks. He didn't cite the assessment documents. He simply said they were ready. That's what 1 in 30 looks like from the crew's side. Not a number that stops you, but a number you choose to live with. Because what's on the other side justifies what it costs to get there. And yet, there's a dimension of that number that remains philosophically uncomfortable, even if you accept the crew's decision as fully rational and fully informed. The 1 in 30 threshold was not set by the astronauts. It was set by the institution that sends them. And the institution that defines acceptable risk is not the same entity that ultimately pays the price if that threshold proves insufficient. There is a structural asymmetry between who accepts the risk and who absorbs its consequences, one that cannot be resolved by more documentation, more transparency, or better modeling. That's not a criticism specific to NASA. It's a description of the fundamental structure of every human exploration program in history, from early naval expeditions to Apollo program to Artemis program. Institutions define acceptable risk in pursuit of objectives. Individuals accept those risks with enough understanding to know what they are accepting. When it works, we call it a historic achievement. When it doesn't, we call it tragedy. Right now, Artemis II is on the side we call achievement, or at least on its way there. The flyby happened, the distance record was broken, the crew emerged from behind the moon with clear voices describing meteor impacts and a solar eclipse no human on Earth had ever seen directly. And when they splashed down off the coast of San Diego on April 10th, the heat shield will have been tested for the first time under the conditions that actually matter. The data it gathers during those 5 minutes of plasma over the Pacific will be the most valuable information available for Artemis III. What Artemis II has done, if it returns successfully, is to demonstrate that the 1 in 30 figure was honest enough to be operational, that the bounded uncertainty architecture defining this program's risk philosophy can sustain a real mission with a real crew in real deep space, that the failure modes not fully anticipated by the analysis were neither frequent enough nor severe enough to end the mission differently. That does not close the question of risk for subsequent missions. It closes it partially for the failure modes that this mission had the opportunity to reveal. Those that have not yet been revealed are still there, unknown, waiting for the conditions that will make them visible. That is the enduring nature of crewed deep space. Each mission turns some unknowns into knowns, and cannot know in advance how many unknowns remain. But the crew of Artemis II went into deep space knowing all of that, knowing the numbers, knowing the coupled failure modes we described in this video. knowing that the heat shield had not been replaced, that there was no lifeboat, that there would be 40 minutes of silence over the far side of the moon, and that the sun was still not quiet. And they went anyway. Not in spite of understanding the risk, precisely because they understood it, because they had spent years learning how to operate within it, and because they concluded that what lay on the other side of that risk was worth the cost of accepting it. That does not solve any of the engineering problems we've described. It does not make the heat shield more robust, or the blackout shorter, or the solar storm less unpredictable. But it does say something about why human beings keep sending other human beings to the most dangerous place that exists, with imperfect hardware, with incomplete information, with risk thresholds that no commercial airline passenger would ever accept without thinking twice. The answer is not in the risk assessment documents. It is in what Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen did on April 1st, 2026, when the countdown reached 0 and the engines ignited. They went.